You know, there's this hidden force, a secret science, that shapes pretty much everything. And I mean everything, from the tallest skyscraper to the most distant star. Today, we're pulling back the curtain on the science of bending.
So what does connect a skyscraper, a microchip, and a distant star? It totally sounds like the beginning of a joke, right? You've got this huge building, this teeny tiny piece of technology, and a star. I mean, come on, what's the link? Well, the answer is actually this one single principle that controls how all of them, every single one, reacts when a force is applied.
And that principle, it's called deflection. Okay, I know it sounds a little technical, but all it really is the science of how things bend or stretch or even warp. It's about how stuff, any stuff, pushes back when you push on it. And trust me, once you get what it is, you're going to start seeing it everywhere. And I mean, everywhere.
So, we're going to dive into what's called deflection analysis. And look, this isn't just some high-level concept only physicists care about. Nope. This is the actual toolkit, the nuts and bolts that everyone, from engineers to tech gurus to astrophysicists use to, well, build and make sense of the world we live in.
And when I say they use it to understand our world, I'm not exaggerating. I mean everything. The ground you're standing on, the phone you might be holding, if it's a physical thing that has forces pushing or pulling on it, you better believe its deflection matters a lot.
All right, so let's start big. I mean really big. We're talking the massive macro-scale structures that we see every day. Because it turns out understanding how to control this bending, this deflection, is the secret sauce to how they even exist in the first place.
Think about it. Every single bridge you've ever driven over, like the incredible Chongqing Gaozhou Garden Bridge, is actually designed to bend. Just a little, but it's on purpose. Same for skyscrapers, right? They're built to sway in the wind. Engineers have to calculate the perfect amount of give for pretty much everything. Wind turbine blades, train tracks, you name it. It's all about being flexible enough to not be brittle, but strong enough to not collapse.
And get this, it's not like they just do the math once and call it a day. Oh no, there are systems in place right now constantly measuring these tiny movements, these little bends and sways, 24/7.
And they do that because when you're talking about something as huge as a bridge, that little bit of controlled bending is what makes it strong. It's the difference between flexing and snapping. It's literally what keeps us safe.
Okay, so we've been talking about city-sized structures. Now, I want you to completely flip that. Let's shrink way, way down into the microscopic world. We're going inside our gadgets, our tech, because that exact same principle is running the show in there too. But here's the crazy part. It's the same science, but for a totally opposite reason. Down at this tiny scale, managing a little bend isn't about stopping something from breaking. It's actually what makes the thing work in the first place.
Yeah, it's really two sides of the same coin. For a bridge, if it bends too much, that's a disaster. But for, say, a tiny little micro actuator inside your phone, that precise controlled bend is its job. One is all about safety and preventing failure. The other is all about precision and making something happen. Just look at all the places this pops up inside the tech we use every day. To make a computer chip, you have to prevent even the tiniest microscopic warp. But then, the little gadgets inside your phone that make it vibrate or sense when you turn it, those work because they are designed to bend in a very specific, controlled way. It's mind-blowing, really.
Okay, so we've gone from huge to tiny. But believe it or not, we're just getting started. The story of deflection goes to some places you would absolutely never expect.
All right, here's one. Anyone ever have braces? Well, your orthodontist is basically a deflection engineer. Seriously, they are calculating the exact force and bend in those wires to slowly, carefully move your teeth where they need to go. That's deflection in action, right in your mouth.
Okay, this one is probably my favorite. Even light bends. It's incredible. Astrophysicists actually study the deflection of light from distant stars as it curves around massive things like galaxies. Einstein himself predicted this. It's called gravitational lensing, and we're using this core idea of bending to understand, well, the fabric of the universe itself. How cool is that?
And then we can snap right back from the cosmos to your living room. You know how a curtain hangs? Or how a t-shirt drapes over a chair? Yep, you guessed it. That's just deflection. The fabric bending under its own weight.
It gets even wilder. People in biomechanics use it to analyze things like martial arts. They study the lightning-fast hand movements, looking at how the body and limbs bend and react at incredible speeds. Honestly, the list is endless. It's used in designing medical implants that need to flex with your body.
It's used to fine-tune the flaps on a plane's wing. And really importantly, it's what makes crumple zones in cars work. They're designed to bend and absorb the impact of a crash, which keeps you safer. It's everywhere.
So you see the pattern, right? From the biggest things we can build to the tiniest things we can imagine. And even in nature and out in space, this one simple idea, this science of bending, really does connect it all.
And this is a great way to see that whole journey laid out. We started at the macro level with bridges, then we zoomed way into the micro level with computer chips. We saw it on a human scale with braces, and then we blasted off to the cosmic scale with starlight. It's an incredible range.
You know, this quote just nails it. From the stability of a skyscraper to the path of light from a distant star, the science of bending connects the universe. It's like a universal language for how things deal with forces, no matter what or where they are.
So at the end of the day, what's the big idea here? It's that deflection isn't just some boring engineering term. It's a lens, a whole new way of looking at the world. When you start thinking about it, you start to see why things are designed the way they are, how they actually work, and, how it's all kind of connected.
It's a really powerful idea. So now that you see it everywhere, what are you going to look at differently? The next time you see a bridge flexing under traffic, a tree branch bending in the wind, or even just look up at the stars, maybe you'll see that hidden science doing its thing.